Hello.
We're on chapter 3. We went through a plane wall, the heat equation. If we integrate it twice, we get this temperature distribution. We can take the derivative of that and get this, right? For heat flux, we can rearrange for heat thermal resistances, do a thermal resistance network, right? There's contact resistance, composite wall where we just sum up our resistors, and then we can get a total resistance across the whole thing. If we want to, we could put that into an overall heat transfer coefficient, series and parallel. Tube, we were on, do the same thing, heat flux, and we looked at now the temperature distribution is a curved line, right? When we integrate twice, we get the temperature distribution at the bottom. Take the derivative, we get our heat flux or per unit length values, and there's our conduction resistance equations. All right, so then we can have a composite wall and sum up, and same in the cylindrical coordinates, and sum up the different resistors, right? So you can get an overall contact resistance and overall resistance. The one thing I wanted to say is if we sum up the resistances here, so from this side we're summing up all these resistors, right? We get a total resistance. We can relate this back to an overall heat transfer coefficient. Well, this resistance, this total resistance, is a constant value. So that is constant. That means U times A is a constant, okay, in cylindrical coordinates. In spherical, that area doesn't change. So the overall, in plane walls, that area doesn't change. So the overall heat transfer coefficient doesn't change also in the plane wall because that cross-sectional area is the same. But in cylindrical coordinates, you can see as we go outward in this case, the cross-sectional area changes. So that means that overall heat transfer coefficient U is tied to an interface. So even though U times A, this value is always constant, if you're looking for that individual value of U, it is tied to the total. It is tied to that area. Okay. The other thing you can see here is the you see the convection here. You see the materials A's resistance, B and C, and they have different thermal conductivities that they've done in these plots, but you can see those curved lines again, right? It has a curved line. It's not a linear line as in the plane wall case. Spherical. So with the spherical shell, so you're basically going in the radial direction. So we have our 1D, again, our steady state, our volumetric heat generation, that's 0, and constant properties for constant K. So we get down to our equation here, and if we think of heat flux in the radial direction, that's just this, okay? So the heat flux, if we substitute in the TDR in here, we're going to have Q, this is going to end up being Q prime over K, right? So what'll happen is you see it's not constant, the heat flux, right? It's changing with R squared, okay? And that's again because the cross-sectional area changes. See here, you see the surface area that heat would flow if it's going in to out. And then here, that same amount of heat, because conservation energy tells us that the amount of heat can't change. But the cross-sectional area gets bigger and bigger and bigger, so it changes the heat flux. Okay. Now, if we integrate this heat equation twice, right? So again, it's a second order with R, right? We have dr and then we have dr again. So if we integrate it twice, put in the two boundary conditions of knowing the surface temperature there and knowing the surface temperature there, we get the equation you see down here. Okay, and you can see how it's a function of the radius there. And we can, just like with the plane wall and the cylindrical, we can take our derivative, put it into our heat flux equation, we get this, and then for our heat, we get this. So it's basically putting in that cross-sectional area back in there. Okay. And then the thermal resistance through conduction of the spherical wall is that equation. Okay, so we have now one for each. Okay? And the same thing can be done for the universal overall heat transfer coefficient. And again, this is constant, so those are equal, but the cross area changes, so U will change with the area. All these resistances are in table 3.3. They have it for plane wall, cylindrical, and spherical coordinates. They have equations for the heat equation, the thermal resistance, so this R for each of those. So it has a few different equations there that are nice, good, that we basically went through here for the different coordinate systems, nice and summarized right in that table. So that's a good table to kind of bookmark and or print out, or whichever way you want to go about it. All right, so let's do some quicker examples. So 3.23. Let me go find this. The performance of gas turbine engines may be improved by increasing the tolerance of the turbine blades to hot gases emerging from the combustor. One approach to achieving high operating temperatures involves application of a thermal barrier coating, TBC, to the exterior surface of a blade while passing cooling air through the blade. Typically, the blade is made from high temperature superalloy, such as Inconel, which has a thermal conductivity of 25 watts per meters Kelvin, while a ceramic such as zirconia with K of 1.3 watts per meters Kelvin is used as the thermal barrier coating. And then they give the schematic you see on the top here. And then they say, consider conditions for which hot gases at T infinity outer is 1700 Kelvin, and cooling air at T infinity inner is 400 Kelvin, provide outer and inner surface convection coefficients of 1000 and 500 watts per meter squared Kelvin respectively. If a 0.5 millimeter thick zirconia TBC, so thermal barrier coating, is attached to a 5 millimeter thick Inconel blade wall by means of a metallic bonding agent, which provides an interfacial thermal resistance of R double prime 10 to the negative fourth meter squared Kelvin per watt, can the Inconel be maintained at a temperature that is below its maximum allowable value of 1250 Kelvin? Radiation effects may be neglected, and the turbine blade may be approximated as plane wall. Plot the temperature distribution with and without the TBC. Are there any limitations to the thickness of the TBC? Okay. All right, so we have this setup. We have the hot gases on the outside of a turbine blade, right? And from thermo, we know that we want to increase the hot gas temperature as much as possible because the Carnot cycle tells us that'll increase the thermal efficiency of a gas turbine engine, right, of a heat engine. So here's now trying to make the temperature hotter so that we can have a little bit higher efficiency. So that's with potentially with the thermal barrier coating. All right, so we're given the hot gas temperature convection coefficient. We have cooling air running through the blade. All right, so there also have some cooling air running through the blade to try to keep the temperature down too. And it has a temperature and a convection coefficient. And we have the blade as the super alloy. Okay, and then there's the conditions of. All right, now we put a bonding agent to attach the thermal barrier coating on, okay, to help with the temperatures again for the super alloy, and we got to see whether that helps or not. Okay, the Inconel, which is the super alloy, has a temperature that it can max have as 1250 Kelvin. Okay, they give us, the convection coefficient T infinity on the outside, convection coefficient T infinity on the inside. We have thicknesses. We have the thermal conductivity of each, okay? And then to attach the zirconia to the super alloy right here, we see there's a contact resistance that was given, okay, for connecting those two together. All right, so if we think about this, of what's going on, it has the one-dimensional, right, steady state. It ends up being a composite wall because we have multiple layers, constant properties, negligible radiation. There's also no volumetric heat generation. Okay. So if we look at this, that if those things apply, then we can apply the equations that we have developed in our slides. If any of those things are not valid, steady state, 1D, no volumetric heat generation, constant properties, so constant K in this case. So any one of these, if it's not valid, we have to go back to the heat equation. Okay, so that's why if it's not 1D, that's maybe 2D, 3D, which is chapter 4, which we're going to end up skipping. But if it's not steady state, that's chapter 5, where we go back to the heat equation and try to solve it differently. Okay, if there's no Q dot, that's actually, if there's volumetric heat generation, now that's the second part of chapter 3 that we're going to actually skip over that one. There's a third part to chapter 3. So you saw a little bit of the volumetric heat generation though in chapter 2. But that would be that part. Okay, so you can't. These equations are valid that we use with these assumptions. Okay. All right. So if we look at this, we have T infinity, so moving left to right. So with these things being valid, of those assumptions, we can set up a thermal circuit. Okay. So we have our thermal circuit. All right, we're starting on the inside. We're right here. We have convection. So outer convection. Okay, resistance. Then, so that gets us to right here. Then we have zirconia's resistance. Okay. Then we get to our contact resistance, which is across this. Okay. Then we have, on the other side now, we have our Inconel. So that's our Inconel's resistance. And then we have convection resistance on the inside. Okay, and that gets us to T infinity on the inside. Okay, so the other thing we can draw here is our heat transfer. So in this case, it's heat flux because we don't have any cross-sectional area. So we have our heat flowing from left to right, okay? High temperature to low temperature. So part A, or the first, I guess the only part really that we're going to be covering is looking at the maximum blade temperature with and without the thermal barrier coating. Okay, so if that's the case, where do we start in this problem? We have our thermal circuit. So now it's just looking at our thermal circuit. How can we determine the blade temperature? And when they're talking about the blade temperature, they're talking about the superalloy, okay, the Inconel. Any ideas? All right, so like usual, I'll do this one and then we'll do the ones where we walk it through. But here we see, we don't know this, right? Yeah, we don't know heat flux. They gave us all kinds of values. So they gave us enough for convection. We know the thickness and okay, so we know our resistance. This is our resistance equation there. They gave us this, they gave us this, they gave us this. So we know that, okay? We also know T infinity inside and T infinity outside. So we know those points on this thermal circuit. So what we can do is just go across the thermal circuit from those points, since those are the ones we know. And we basically just do the total resistance, since we're going across the whole thing, because that's the temperatures we know. Then we are adding up all 5 of these resistances to get us our total. Okay, and that's what you see in the equation right here. Okay, there's our total resistance. If we add up all those resistors, so that's the equations added together, plug in all those values, we get our total resistance. All right, so that gets us the heat flux. So now, if we go back to our thermal circuit, now we know the heat flux. And that's the same all the way through our resistors, okay? So now it doesn't matter where we want to, we can take a delta T, we just need to take the resistance across any of those locations. So if we're looking for this temperature and this temperature, right, because that's the Inconel's temperature on each surface, we know this temperature, we don't know this one, so we could take it across here, okay? We could have also taken it from here to here, because we know this temperature too, and we know the heat flux, which will be the same across those. So if we're doing it across this one to this one, okay, we just have this one resistance, and that's what you see here. They're just doing this. The cross that delta T that I showed you here, it's across, then it's that resistance across it, okay? So plug that in, we know this, we know this, we know this, so the only thing is the temperature of the surface. So we get the inner surface of the Inconel's temperature. Now we want the outer surface, and again, we don't know this, so we just have to take it across a temperature that we do know, since we know the heat flux. So we could take it from across this, we could take it across here, we could take it across here. You just got to use the resistance that goes accordingly with where you're taking it across from. Solution shows this one from here to here. And that's what you see right here with it rearranged. They just did. Grab a little extra space here. So they have the 2 resistors, because we're going across from here to here. One resistor, another. So adding those 2 resistors across that delta T. And we know this one. We know this. We know our resistance. So we don't know the temperature. So we get 1174 Kelvin. Without the thermal barrier coating, that's basically saying that we don't have the bonding agent here, and we don't have the thermal barrier coating. So you just have, let's rewrite our resistor network. So we have convection resistor, we have the Inconel, and then we have convection on the inside. So we have this, okay? And we want, again, these temperatures. So we take it across here. We take it across from here to here to get our heat flux in this new situation, okay? And then we can take it across the resistor here to here to get that temperature, and here to here again to get that temperature, okay? So we get our heat flux from this total delta T. So delta T and its total resistance, we get our new heat flux. Now we take it across here to here to get the temperature on that surface, inside surface, and the outside surface. Okay, so we go across here, and then we go across here to get that temperature. Okay, so in this case, we see ranges from 1212 to 1295 to 1293, which ends up being too high because they said it needs a 1250 as the max that the superalloy, the Inconel, can see. So the thermal barrier coating allowed the Inconel to only see up to 1174 Kelvin. So it, dropped the temperature over 100 degrees, over about 120 degrees Celsius, degrees Kelvin. Okay, so that says we need to use thermal barrier coating, but at least for temperature, but we need to be careful about thermal barrier coating's reliability and such. Okay. Any questions? Okay. Another example. We have 3.56. A composite spherical shell of inner radius R1 is equal to 0.25 meters. Is constructed from lead of outer radius R2 of 0.3 meters and AISI 302 stainless steel of outer radius R3 0.31 meters. The cavity is filled with radioactive waste that generate heat at a rate of Q dot equal to 5 times 10 to the 5th watts per meters cubed. It is proposed to submerge the container in oceanic waters that are at a temperature of T infinity of 10 degrees Celsius and provide a uniform convection coefficient of 500 watts per meter squared Kelvin at the outer surface of the container. Are there any problems associated with this proposal? Okay, and any problems, we're more just kind of looking at it. The problems being, are there any heat transfer, thermal related problems? Okay. All right, so they didn't give us a schematic, but you see it here kind of drawn. We have radioactive waste inside, right here, right? Then we have a lead. It's spherical, right? It's a spherical shell. We have lead. Then we have, so that's lead, and then we have stainless steel layer. Okay, and they give us the radiuses for each, right? And then they also gave us the volumetric heat generation value. Okay. All right, so if they are, our assumptions are saying 1D right here, steady state, constant properties, negligible contact resistance between the lead and the stainless steel. There should also be that we have no heat generation, right? Well, in this case, they're giving us a radioactive waste heat generation rate, the volumetric heat generation rate. It's right there. And then they still draw a thermal circuit, right? Why is it valid in this case that we can draw a thermal circuit even though we have a volumetric heat generation?
Does it have to do with like the boundary of your system?
Yes. Okay, so if you see this thermal circuit, that temperature 1 is right here. That's T1. Okay, and that's T3 right here. So the radioactive waste is occurring inside here. So if we wanted to know, let's say we wanted to know the temperature distribution inside the radioactive waste, then we would have to go back to the heat equation and apply our knowledge from chapter 2 and integrate it with keeping the heat equation and keeping the volumetric heat generation rate and in there. But we're taking it starting where the heat generation rate ends and only doing it through those lead and stainless steel. Okay, so that's why it's valid. Okay, so then that means if we look at our thermal circuit, so they already drew it for us, so that we have our help there. We have lead, the resistance right here. We have the stainless steel's resistance, and then we have convection on the outside. Oops, let's draw a better R here. Okay, and the temperature 1 is the inside surface of lead. Temperature 2 is the outside surface of lead or the inside surface of stainless steel. 3 is the outside surface of the stainless steel, right? And then T infinity is the oceanic water's temperature. Okay. These resistor equations can be found just by using table 3.3 that I mentioned. Okay. So the other thing we draw is our Q, right? So Q is coming from the radioactive waste. Okay. So in this case, we have Q. So if Q is coming from the radioactive waste, we're just basically taking volumetric heat generation rate of that radioactive waste and multiple times the volume you have there of radioactive waste. And that gets us the heat that has to go through. The only place for the heat to go is through the lead and the stainless steel. Okay. And this is where you see the volume. Okay. That means we get Q from that. Now, temperature-wise, we have T infinity, right? We don't have any other temperature, but we now have Q, right? So if we use this, we can solve for Q. So if we know Q and we know T infinity, we can just take a thermal circuit across anything and find the temperatures. Okay, so in this case, we're going to look for T1. Okay. Oh, the other thing I should say, property-wise, they didn't give it to us directly, but they gave us the type of stainless steel in the question. So we can go in the back of the table and look at it, and they give us lead, and go in the back of the table and look at and get our values. All right. So if we have that, we can calculate all our resistances. Okay. So here they are. We got 1, 2, 3. So lead, stainless steel, convection, right? So our total resistance is that across all of the shell. Our heat rate from the radioactive waste is there, okay, solved. And now we're just taking our Q of our T1 minus T infinity over the R total. And we solve for T. So we have T infinity, we have R total, we have Q now. Okay, so in that case, we get a temperature of 405 Kelvin, which is less than the melting point of lead, which is 601. Okay. So they're saying, from a thermal standpoint, the proposal's adequate. Why didn't they check the temperature at, say, 2 or 3 and see if temperature 2 was going to be melting for the lead, or melting temperature for the lead or stainless steel, or T3 was going to be the melting point of the lead, or of the stainless steel, sorry. Any reason why they only really checked 1 and not 2 and 3?
The melting point of lead is lower.
Right. So, but then why did they check 2? T2? Because that still shows the temperature of the lead, right? But yes, so one point is we do not have to check stainless steel's melting point's much higher, right? It's maybe 1,000 Kelvin, 1,200 Kelvin, somewhere in there. So we don't have to check it, right? But T2 is still of the lead. So it just comes from understanding, you know, if our heat is going from T1 to T infinity here, this heat that's conducting and then going through convection is going from high to low, right? So T2 has to be lower than T1 for heat to flow from T1 to T2. So temperature 2 is definitely going to be lower than temperature 1. So we do not need to check T2. T1 is the highest temperature. And if it's below the melting point of lead, stainless steel, it's going to be fine all the way through in the other locations. Okay.
I had a question for when you have like multiple materials like this though, but it's constant properties. It's constant, like each material's constant properties. Or
correct.
Okay.
Yeah. Yeah, basically we're solving the heat equation. That's what this thermal circuit is solving the heat equation from here to here. You know, and solving the heat equation, putting it into Fourier's law from here to here with constant properties, then from here to here with constant properties, and then from here to here with constant properties. So although yes, it does change from, you know, 1 to infinity, it's this right here comes from one solution of the heat equation and then putting it into Fourier's law. This right here comes from it. Okay, so forth. Okay. Good question. All right, so let's do some examples